Hello, and welcome to Notes 2020. Thank you for joining us today. I am Melissa from the New York City chapter of PyLadies. Our group organizes events to share knowledge in the usage of Python, while also encouraging women to become active participants and leaders in the Python open source community. I'd like to introduce our next speaker. Klaus Blass is a survey and IT consultant at the World Bank, and will be presenting a survey as a graph. Klaus is a consultant in the Development Data Group at the World Bank, assisting national statistical offices worldwide to conduct surveys and censuses. Thank you and welcome, Klaus.
Hello, I'm Klaus Blass, and I'm going to talk about how to represent a survey as a graph in Neo4j today. Surveys come in all kinds of flavors. Household budget surveys, agricultural surveys, etc. But there's one thing that divides surveys in two classes. That's cross-sectional surveys, where you capture the state of a population at a single moment in time, and longitudinal surveys, which are repeated at regular intervals, where you monitor a population over time. In the past, surveys were done on paper forms with subsequent data entry into a computer. Nowadays, we use computer-assisted technology, copy systems, where the questionnaire is implemented on tablets, and you collect the data on a tablet, and they are regularly sent to a server over the internet. And at the end, your data are already in digital format on the server. We are using Survey Solutions, which is one of the major copy platforms today. It has been developed by the World Bank and has been used in thousands of surveys and censuses in 175 countries so far. It's absolutely free software to anybody who wants to use it. Now, this is a typical interview situation in a Western African country. Note the tablet where the enumerator marks his responses. Now, at the end of the survey, we got all the data on the server as a set of files or tables, table for households, for household members, revenues and expenses, etc. Our survey is about a health and demographic surveillance system, or HDSS, where we are monitoring the state of a population over time. Data about demography, health, the wealth of the household, assets and animals they own, migration events. The HDSS in question is the NUNA HDSS in Burkina Faso, which is administered by the NUNA Health Research Center in partnership with the Heidelberg Institute of Global Health. It comprises of 59 villages with around 14,000 households and 115,000 people. Here you can see the 59 villages represented as little red dots. Now, let's have a look at one of our data tables. This one is the household table, and this is raw data. It's not a carefully prepared data set published by a government agency. You notice the cryptic variable names like Q101 and another column Q101 other. So you see that one question may occupy multiple columns. And you notice that most of the data collected are numeric. This is because the majority of our questions are multiple choice questions, where the respondent is presented a list of options, and he selects one or more of these options, and the system only records the code of the option that was responded. Here's another view of the same households table, and it shows some strange numbers which are missing values for questions that have not been answered. Now, each data table has got a companion file which explains the labels of the codes in the main data table. So here, for example, question Q107, which is about building materials for a floor of the dwelling. And you can see code 2 means polished wood, 4 is vinyl, 5 is cement, etc. You also notice that the language of the survey was French. Now we can see that the data in the tables are arranged not for clarity from a human reader's point of view, but for completeness. All the responses are recorded with all detail precisely in these tables. We notice that a single variable may occupy several columns and that the data in the tables are just codes, the labels being in different files. So we can see that just loading these data with a general load utility is not an option. We have to write a custom loading program. So I wrote a custom Java loader. The basic structure is simple. You instantiate a database driver, supply the server port and your credentials, and you write a method or function which opens a database session, starts a transaction, runs a Cypher query, commits the transaction, and receives the results. This is an actual example from my code for loading the household data. The first object is just a Cypher query implemented in Java, and the second object is a method or function which will step through the file line by line and execute the Cypher query, supplying data from the line in the file as parameters to the properties being recorded. Now this way we load all our nodes and create relationships between them, villages, compounds, households, members, etc. And after a short time, we already have a nice representation of these data in Neo4j. Here you can see one of the villages at the center. This village points to a couple of little red nodes, which are compounds, and each compound points to one or more households, and each household is connected with a number of household members, the green nodes. Clicking one of these nodes will show you in the browser the full set of properties stored for this node. Now, while we do this, we come across some bad data in our raw data files. And as a survey consultant, I have a principle to never throw away any survey data. For example, we have found some empty compounds without any households. Now, this is something that cannot exist because a compound is just a collection of households. But they are there, they have GPS coordinates recorded. I don't want to throw these data away, but I don't want to consider them when I query compounds, because compounds without households cannot exist. Our solution was to relabel those empty compounds from compounds to ghost compounds. Now they will no longer show up in any compound-related queries, but I have them as ghost compounds whenever I need to query them. A similar case are reported deaths. Members who have died should no longer be considered household members. But of course, we want to remember all their data and the households they belong to. Again, the solution was to relabel those nodes from members to deceased. Now, I mentioned before that a lot of the questions in the survey are multiple choice questions. So on the right, you see a list of options for the building materials for the floor of a dwelling, and the respondent can select one or more of these options. And I want to store them in the database and be able later to query these properties, either by code, if I know it, or by the description. Our solution was to store the code and the description in a single string or property. Now the problem is how we have to decide how to query by either the code or the description. I can show you here at the bottom, you see our floor material property. It has code 5 and ciment, which is French for cement. The solution was to write our own functions. This is a very powerful feature in Neo4j. You can extend the Cypher query language with your own functions written in Java with the full functionality of Java. So I wrote a function codeof, which takes a property name and a code, and a second function called includes, which again takes a property and a part of the description of that property. This is the actual implementation of this second includes function. That's all it takes. It returns a value of true if a match is found, false otherwise. It normalizes both the property description and the keyword, the search term, then splits the description into words and tries to find a match between any of the words and the search string. If it finds a match, it returns true. No, we had more cases where we needed user-defined functions, for example, functions for partial dates. In African countries, people usually don't remember their full birth date. Many of the older ones only remember the year they were born. So we had to write new functions for handling partial dates with our own assumptions about the missing month or day components. And another example was a similar function, similarity function, which compares two strings, and you can specify a Liebenstein distance, which allows a match if there are minor differences. Here we allow for differences between the two strings in 2 positions, so it will match the English solar and the French solaire. The most complex question to implement are the ordered multiple response questions. So on the right-hand side, you have an example. This is a screenshot from the tablet of a question about the toilet types used by the household. The tablet will record all the answers, and in addition, it will record the order in which the answers were given. All this is later in the data. So how does our data look like? For this question, we see that we get several columns, several variables, one for each toilet type, and each row represents one household. So household 1 just got a toilet type 4. Household 2 got a toilet type 3, but the third household got a toilet type 3 and a toilet type 4. So how do we represent this as properties in our database? You can look here at the bottom. We have a property called toilet 1, which takes the first option selected by the household. If he selected a second option, we create a property toilet 2, where we store the second option. And if he should use a third toilet type, we create a toilet 3 property. Now we have longitudinal data in our survey. Take the example of pregnancies. Pregnancies differ during survey rounds. A household member may be pregnant during one survey round and not during the next one. We made the pregnancy events as implemented them as nodes. So they could later also be linked to an outcome, like a newly born member. Now we need a way to identify the pregnancy by the round they were reported. Our solution was to use multiple labels. So any pregnancy gets a pregnancy label, and in addition, it gets a label for the round when it was reported. So later on, we can query by pregnancies in general or pregnancies in a specific round. And a last important issue is migration, people arriving or leaving the population. First was we had to make a decision, should we make it a node, a property, or a relationship? A node like the pregnancy node. We decided for the relationship because Neo4j, in Neo4j, relationships are first-class members, so they also can take properties. And we can use these properties for the relationships to record the date of the migration, the reason for the migration, etc. So if you look at the example at the right, we see a number of people, household members who have immigrated from outside the HDSS, but from the country. They're all household members with one exception. This guy has immigrated from outside the HDSS, but is not a household member. Actually, he has later returned to the place he came from, so we relabel him as a visitor. And here we've got some emigrations to Ivory Coast, another country. And we can see this person has emigrated to Ivory Coast and he has been relabeled as an emigrant. But here is a household member, a green node. Although he has emigrated to Ivory Coast, he's still a household member. Well, this means he has later returned to his household. And all the data about the date when he returned, the reason why he returned, etc., are stored as properties in the relationship. Here's a final example of how nicely the browser can show the immigration patterns. This is the result of a simple query about all emigrations from the HDSS to some place outside the country, to some other country. And you can see the major destinations for immigrants like Ivory Coast here, Mali here, and you can see major sources of emigration like Nuna, the largest village in the HDSS, and other villages as well. So what I have tried to show you here is how to represent the data from a longitudinal survey as a graph and how to use some of the features in Neo4j to achieve this in a comfortable way. Thank you for your attention.